Let us learn about the different types of mirrors, their properties and their applications. A mirror is a reflecting surface that causes an image to be formed. The reflecting surface is formed by coating it with silver and then painting it with red paint to protect the silver coating. Mirrors are of two kinds: plain mirror and spherical mirror. A plain mirror is a plain glass sheet, one side of which has the silver coating. This makes the other side of the glass sheet reflecting, acting as a mirror. A spherical mirror is a part of a spherical reflecting surface, generally made of glass. One surface of the glass is silver coated. Its cross section is an arc of a circle. Spherical mirrors are of two types: concave and convex. A spherical mirror that has its inner side or concave side polished is called a concave mirror. Concave mirrors are also called converging mirrors, as incident rays of light parallel to the principal axis converge at a single point after reflection. A spherical mirror that has its outer side or convex surface polished is called a convex mirror. It is also called diverging mirror, as the incident rays of light parallel to the principal axis appear to be diverging from a single point after reflection. Concepts related to spherical mirrors. Center of curvature, represented by C. The center of the sphere, of which the mirror is a part, is called the center of curvature, C, of the mirror. Pole, represented by P. The center of a spherical mirror is called the pole P of the mirror. Radius of curvature, represented by R. The radius of the sphere of which the mirror is a part, or the distance between the center of curvature and pole of the mirror, is called the radius of curvature, R, of the mirror. Principal axis. The straight line passing through the pole and the center of curvature of a spherical mirror is called the principal axis of the mirror. Focus of a concave mirror, represented by F. The rays of light parallel to the principal axis on reflection from a concave mirror meet in front of the mirror at a single point on the principal axis. This point is called the focus F of the concave mirror. Focus of a convex mirror, represented by F. The rays of light parallel to the principal axis appear to meet behind the mirror at or get diverged from a single point on the principal axis. This point is called the focus F of the convex mirror. Focal length, represented by small f of a spherical mirror. The distance between the pole and the focus of a spherical mirror is called the focal length, small f, of the mirror. The focal length is half of the radius of curvature. That is, focal length is equal to r upon 2. Light. Light is a form of electromagnetic radiation that produces the sensation of vision. When light that falls on an object is reflected back and reaches our eyes, we are able to see the object. An image of an object is produced by reflection of light from the object and their reception on a surface. An image can be real or virtual. Real image. An image formed by converging of rays at a point is called a real image. So, it can be obtained on a screen. A real image is inverted. Virtual image. An image from which the reflected or refracted rays of light appear to diverge is called a virtual image. So, it cannot be obtained on a screen. A virtual image is erect. The image made by a plane mirror is a virtual image. Convergence and divergence of light. Convergence of light. When light rays meet at a single point, it is called convergence of light. When we want to concentrate light at a point, converging beam of light is used. For example, in searchlights, headlamps, torch used by doctors to examine teeth, ears, eyes, etc. Divergence of light. When light rays from the same point source are spread away from each other, it is called divergence of light. When we want to spread light from a source, diverging beam is used. For example, in street lights, table lamps, as a rear view mirror in four-wheelers, motorcycles, etc. Images formed by a concave mirror. The nature, position, and size of the image formed depends upon the distance of the object from the reflecting surface. Rules for drawing ray diagrams are based on laws of reflection. Images formed by a mirror can be studied with the help of a ray diagram. Rule 1. If the incident ray is parallel to the principal axis, then the reflected ray passes through the focus. Rule 2. If the incident ray passes through the focus, then the reflected ray is parallel to the principal axis. Rule 3. If the incident ray passes through the center of curvature, the reflected ray traces the same path. Image formation by a concave mirror with respect to the position of object. When the object is at infinity, the image is formed at the focus F. The image is highly diminished, real and inverted. When the object is between infinity and the center of curvature, the image is formed between the focus F and the center of curvature C. The image is diminished, real and inverted. When the object is at the center of curvature C, the image is formed at the center of curvature C. The image is of the same size as that of the object, is real and inverted. When the object is between focus F and the center of curvature C, the image is formed beyond the center of curvature C. The image is magnified, real and inverted. When the object is at the principal focus F, the image is formed at infinity. The image is highly magnified, real and inverted. When the object is between the pole and the principal focus, the image is formed behind the mirror. The image is magnified, virtual and erect. The table shows the summary of image formation by concave mirror. Sign convention for reflection of light by a spherical mirror. The sign conventions. According to the new Cartesian sign convention, the pole P of a spherical mirror is taken as the origin and the principal axis is taken as x-axis of the coordinate system. The sign conventions are as follows. 1. The object is always placed on the left side of the mirror. 2. All distances parallel to the principal axis are measured from the pole of the mirror. 3. All distances measured to the right of the origin pole are taken as positive, while distances measured to the left of the origin pole are taken as negative. 4. Distances measured perpendicular to and above the principal axis are taken as positive. 5. Distances measured perpendicular to and below the principal axis are taken as negative. 6. The focal length of a convex mirror is positive, while that of a concave mirror is negative. Mirror formula. Mirror formula. The relationship between the object distance u, image distance v, and focal length f of a spherical mirror is called the mirror formula and is given as 1 upon v plus 1 upon u is equal to 1 upon f. Keeping the known values according to sign convention, any of the unknown component can be calculated. Magnification by a spherical mirror. Magnification produced by a spherical mirror is expressed as the ratio of the height of the image, h2, to the height of the object, h1. It gives the relative extent to which the image of an object is magnified with respect to the object size. As the object is usually placed above the principal axis, h1 is taken as positive. h2 is taken as positive for a virtual image, being above the principal axis, and negative for a real image, being below the principal axis. Example: for a concave mirror with f equals to -3 centimeter, object distance u equals to -10 centimeter, and the height of the object h1 is equal to 2 centimeter. Find the position, size, and nature of the image. Given object distance u equals to -10 centimeters, focal length equals to f equals to -3 centimeters, object size equals to h1 equals to 2 centimeters. We have to find out the distance of the image from the pole V and the height of the image h2. 1. To find out the distance of the image from the pole, we use the formula 1 upon V plus 1 upon U is equal to 1 upon F. Therefore, 1 upon V is equal to 1 upon F minus 1 upon U. Putting the values of F and U, we have 1 upon V is equal to 1 upon -3 minus 1 upon -10. Calculating this, we get 1 upon V is equal to -7 upon 30. Therefore, V is equal to -30 upon 7. Therefore, V equals to -4.29 centimeters. Thus, the image is formed at a distance of 4.29 centimeters from the pole. The negative sign of V shows that the image is formed in front of the mirror. To find out the height of the image, we use the formula M is equal to H2 upon H1 equal to minus V upon U. Thus, H2 is equal to minus V upon U multiplied by H1, or 30 upon 7 divided by minus 10 multiplied by 2 is equal to 6 upon 7 centimeters. Therefore, H2 is equal to 0.86 centimeter. The height of the image is 0.86 centimeter and the negative sign shows that the image is real and inverted and is formed below the principal axis. Applications of spherical mirrors and lenses. A. Uses of concave mirror. A concave mirror has the capability of forming images that can be smaller or larger in size and virtual or erect, depending on the position of the object. Hence, there are many uses of concave mirror. In torches and headlights, a parallel beam of light is obtained by keeping the source of light at the focus. In floodlights, in order to get intense beam of light, the source of light is placed just beyond the center of curvature. Reflecting mirrors for projector lamps. In this case, the object is placed at the center of curvature to obtain an image of the same size. To collect heat radiations in solar devices, the panel to be heated is kept at the focus of the concave mirror, which focuses the radiations from the sun onto the panel. Shaving mirror, dentist's mirror. It produces an erect, virtual and highly magnified image of an object placed between its pole and focus. Solar furnaces. Large concave mirrors are used to concentrate sunlight and produce heat in a solar furnace, which is at the focal point. B. Uses of convex lens. Simple microscope. A single convex lens of small focal length can be used as a simple microscope. Magnification of a simple microscope is about 20 times. It is used by watch repairers, jewelers, etc. Compound microscope. A combination of two convex lenses having short focal lengths are used in compound microscope. It is used in laboratories for observing microorganisms, cells, bacteria, etc. Telescope. A combination of two convex lenses is used in telescopes. An astronomical telescope is used to get detailed view of astronomical bodies like the planets, stars, etc. Optical instruments. Convex lenses are used in different optical instruments like camera, projector, spectrometer, etc. Spectacles. Convex lens is used in spectacles to correct defects like hypermetropia.